Hi all. This is Raj. Uh, Muti gave me an intro about gave intro about myself, so um, won't be doing my intro again. But yeah, I'm talking this talk. I'm presenting with Steve, my colleague, his who built the core optimization service, which we call it as Smart Iceberg Table Optimizer. So we are going to talk about that service today. There are two parts to this talk. I'll talk about what is Iceberg, and Steve is going to talk about the optimization service. Steve, would you like to give us intro about yourself?
Thank you, Raj. Hey everyone, this is Hongyue and I go by Steve. Really happy today to share my learnings about Apache Iceberg with everyone.
Thanks, Steve. So I've covered mine, so let's jump into the talk. So what is Iceberg, right? So Iceberg is not a file format. It is not a data warehouse. It is actually a table format. We call it as table format for metadata tables. We have seen for formats like Parquet, ORC, but what exactly is this table format is? Table format is nothing but how to lay out and organize the files in a table. Right? Let's talk more about comparing with Hive. Hive is a distributed open source data warehouse, which was built for Hadoop over HDFS. It organizes the files as directories, as you can see on the left-hand side, a DB name, table name, and partitions. Within a partition, all the files contribute to that partition, physical partition. Right? If we want to do update operation in Apache Hive, what we do is we read everything and write everything back. Right? So there is no metadata concept. There is no snapshot concept. The metadata is maintained by Hive Metastore, but tables does not maintain any metadata. All the files in the directory, they carry actual data that belongs to that partition or a table. Depends on how the table was designed. When it comes to Iceberg manages in a different way. These files are it follows a tree-like data structure for metadata files to be managed. The metadata layer in the middle of the right side image has these metadata files. So we call it as a metadata layer. So you have data files, you have a metadata layer, and on top of it, you have a catalog, which knows what to refer when there is a query has been filed. It's not maybe we should talk about how these are, but assume that the file maintains actual metadata. So I'm not jumping into what exactly the metadata layer, how these manifest files have been organized and everything, because that's not the purpose of the talk. But we can talk about the metadata layer manages the entire metadata of the tables. So there is a concept called snapshot. Everything is managed by snapshot in Iceberg. We can go a bit deep into snapshot. Snapshot is nothing but every commit operation in Iceberg creates a new snapshot. If you're reading, there is no snapshot. But if you're writing, updating, and deleting, those operations create a snapshot because that changes the files. Reads don't change the files, how they have been organized. But when you do some update operation, CRUD operations, that's when it creates a snapshot. Snapshots refers to the actual data files that are sitting in the physical directory system. The interesting part is when you compare that with Hive, in Iceberg, not all files in the directory contribute to the snapshot. That means when you have an update operation, it creates a new file and it will leave the files which were the legacy files as is in the directory. Right. So that means you have files that are not really part of the snapshot sitting in the same partition directory. Right. So snapshot has the references what files needs to be returned when there is a select query fired by the user. Right. So that's why snapshot and metadata layer is the key to organize the files and maintain the metadata to improve the performance of it. Like in case of Hive, I just mentioned that even if we want to update one particular record, let's take you have a partition of terabyte data. I mean, these are big tables, right? So you have a partition of terabyte data. If you want to update one particular record for GDPR type of use cases, you end up reading 1 petabyte and writing it back. Huge cost when it comes to CPU, because we are just worried about one particular record, but we end up reading everything and writing back everything. Right? In case of Iceberg, we don't have to do that. We just have to read the file that has this particular record, right? Like if you have 1 terabyte with 1,000 files, then we are touching only one file to update one particular record, right? And you improve significant improvement in the performance when you're doing these kind of operations. So, well, let's talk about the benefits of Iceberg. Iceberg is asset compliant. We all know what is asset compliant is. Like it allows concurrent IO read operations. And this type of thing is not very common in traditional data lakehouse, traditional lakes, right? Data lakes. When you talk about Apache Hive is not really asset compliant. Users can perform update and delete operations. I've seen I worked in Hadoop 1.0, 2.0, and 3.x. We used to read and write everything if there is a slowly changing dimension type of operations in data warehousing world. Burning a lot of CPU there because these are big clusters, but still end up doing a lot of operational overhead. So that's a reason why that's a key significant improvement when you're going with Apache Iceberg. Time travel is another cool feature. We have seen significant growing use cases in ML side to test the model with older version of data. Again, the snapshot concept helps to time travel and read tables previous data. The time travel is you have a model, you model tested with one set of data, and data has changed over a period of time. Model is working fine, and after a few days, model has been optimized. Some changes have been done to the model to improve the performance of it. But if you want to see the accuracy of the model needs to be tested. Sometimes needs to be tested with the older version of data, because the older version was the baseline when we released it to the production. Now users can go back to the older version, even though data has changed. They can go back to the older version with the time travel feature and test the model for accuracy purpose. This is a very, very important when you're running large scale machine learning operations at scale. Hidden partitions in traditional data warehousing world, when you stick to one partition, you stick to that partition. No option to change the partition. Right? You want to change the partition, you end up doing recreating the table and reading and writing everything back. Hidden partitioning helps to evolve the partition strategies. Partition strategies improve the reader performance. Readers doesn't have to read everything, right? That's a significant use of the partitioning. And with hidden partitioning, we don't have to stick to one partition strategy here. We have noticed better performance and reliable writing using Iceberg to S3. That's another feature. Iceberg started S3 in late 2020 or 2021, early 2021. AWS announced that S3 is strong consistent. It is not eventual consistent anymore. But Iceberg started providing this from the beginning itself. I'm not sure that we have tested strong consistency with the S3 at really large scale, but with Iceberg, we don't have to worry about writing objects into S3, and it maintains the strong consistency. Let's talk about the last part, sort order, Z order, and min-max stats. If these are the performance boosting techniques. If you want to increase the read performance, the goal is to read as little as possible. We all know partitioning, which falls under this category. With Iceberg, you can achieve further by maintaining column level stats sort order, min-max stats, and Z order. Tables need not to lay out accordingly, but that will help to impact the write performance. And these tables are mostly write once and read off, right? So when you talk about these techniques we'll have to design a table to honor these techniques. The table needs to be designed that way. Once we design that way, while writing the data into the tables, the writer process honors these policies and updates the files or lay out the records in a file accordingly to maintain these column level stats. It's a one-time hit, but these analytical tables are write once and read often, right? So we get significant performance improvements while reading that while reading it. Data retention is key to any organization, not for compliance purpose, but also clean up the data, because we don't want to keep the data forever, right? Iceberg does these. It does this in two ways, right? One is you commit a snapshot with the delete or update operation. That's called soft delete. It does not really delete the data from the disk when you do this operation, but users cannot see it. However, they can go back to a previous snapshot and see what has been deleted, right? So there is a general strategy to maintain how many snapshots that we want to maintain. Steve will talk about that in the later section. Hard delete is what we say that particular section, like you expire a snapshot, then whatever the files which were part of the snapshot will be deleted, and you no longer see those data, and it is disk off, complete disk off. That also involves removing orphan files in this hard delete operation. So it's a two-way strategy, because if we want to support time travel feature, we need to have this snapshotting concept. Apart from column level stats, if we want to increase the query performance that I explained in the previous slide, we need to do data and metadata compaction, right? I mean, you may have small files problem. S3 is not really caused too much of pain when it comes to small files, but HDFS has some amplification, some problem with the small files, because the name node has a limit. If we have too many files, the name node cannot maintain all those. It has a limit because it's a master server architecture. When it comes to S3 does not have small files, but your readers will have a problem. If you're firing a select query, the clients which are triggering this read queries will have a significant impact on the performance when you're dealing with small files. So compaction will relieve from the small file problem, both metadata and data. So metadata is also files in the file system. It is not maintained in RDS type of databases, where if you look at Hive or any other traditional data warehouses, they maintain metadata in the backend store. When it comes to Iceberg maintains the metadata, because the metadata is huge, and it maintains that metadata in the file system itself. Table monitoring. If you're running Iceberg at production, we are running Iceberg at very production, petabyte scale, and a multi-cloud environment. When you're running this, I think the key is to maintain the snapshots, the monitor number of snapshots, what's the table size, number of manifest files are involved, what is the oldest snapshot, and what is the earliest snapshot. This will help us to see the health of the tables in the infrastructure. I would like to hand over this second part of the talk to Steve.
Thank you, Raj. So we're trying to solve the problems above with our smart table optimizer. It's our in-house solution built to manage Iceberg tables at scale. So in the next few slides, we'll talk about it in details. At a high level, you can think the system in three components: as a control planes, persistent layer, and data planes. The control plane is the one who identifies the candidate tables for optimization and write these optimization parameter into the persistent layer, which happen to be a collection of internally managed Iceberg tables. And the data planes on the right-hand side, we use Apache Spark to apply the desired optimization in distributed manners. The end of each executions, data plane also write the such results back to the persistent layer. Next slide, please. The diagram showed us how control plane and data plane work together as a smart table optimizer. Because the control plane needs to integrate with different plugins to source the list of the table candidates, we built the conflict resolution and the deduplication logic into our spec processors. As the name suggests, it will process the table in order, apply the reasonable defaults, and write such record in batch to our own set of Iceberg tables in persistent layers. So earlier I said we choose to using Iceberg as our own storage layer to simplify our dependency graph, given that we are having relatively simple read and write pattern across the control plane data planes, where control planes read tables together, iterating, applied filtering, and then write as a record batch. The data plane will read them one by one and apply desired optimizations. So as you can see on the right-hand side, data plane is much more larger and grouped by its job functionalities. Some of the data plane jobs are parallelizable wrappers on top of Iceberg Spark actions, such as snapshot expirations, orphan file removals, small data files compaction, and manifest rewrites. Those are required and optional maintenance tasks suggested by the Iceberg open source community. There are other monitoring jobs, help provide visibility into our customer adoptions, cost reporting, and performance measuring. This is to make sure that our Iceberg tables stay performant over time. Next slide, please. So one of the questions we ask ourselves is, of the tables found in the catalog worth optimizing with? Optimization helps speed up queries and also provide robust and consistent user experience to interact for the Iceberg table, but at a cost of limited compute resource. We know everyone loves to use Iceberg tables, wanted to get best out of it, but many tables used for experimentation and ready to be thrown away. Even for the production tables, not all the partitions are used so often that warrant full optimization effort. But the answer is actually highly dependent on the business needs. But we figure out what worked best for us in the past is judged by the historical trend. So we built this such integration with Spark, Listener, and the Trino query event to identify the hot tables and partitions who benefit the most from optimization. But we all know past doesn't represent futures. So we also support explicit opt-in and opt-out mechanism so that we can cover the tables we know for certain. Next slide, please. So another problem we noticed that is how can we keep our track of our optimization history? When we started, we only have a few tables under management, and we can do such by searching through the Spark logs. But as many users adopt Iceberg tables, we'll have much more tables under the management. And we decided that we need to persist all this input and output into a corresponding table so that we can query later. In the diagram below, you can see the example of my remove orphan jobs. The Spark action on the right-hand side only need a table identifier and older than timestamp to execute, where we model such parameter as input and number of orphan files removed and Spark application ID as output to persist on the left-hand side. So using Iceberg to store our internal data structure, we can easily debug a particular Spark job failures or track down the aggregate trend over time. And the best part is we can leverage the history of execution to help us decide which execution should we prioritize in the future. Next slide, please. To speak of execution, let's take a deeper look at how Iceberg remove its orphans. Essentially, Iceberg needs to compare what files are tracked in the metadata as desired number of files versus what file exists in the underlying file system as the reality to see is there any divergence between the desired and reality. Together with condition on how old is these files, we came to a decision that if a given orphan should be removed or not. So important to know that this operation actually applied to entire tables, and it can often be the most time-consuming part of our data plane job. Think about our tables of a petabyte scales. We have 1 million of files to iterate over to identify which are considered orphan or not. And also, we realized the orphan time threshold cannot be set too aggressively, as ingestion-based Iceberg often write Iceberg data files under table location before the checkpoint or commit. If we're too aggressive, we are mistakenly sync those files as orphan files, and this will cause the ingestion to fail when writing data into Iceberg tables. Next slide, please. As we can see on the diagram, there are only 8 files tracked by Iceberg metadata, but we found 9 files on the file system. So this particular d3.parquet files is what we consider as orphan here and should be removed by our operations. Given that, we know more data files Iceberg track in a table, the longer it took for it to orphan to be removed. These become more relevant when underlying file system is actually backed by the object storage, just like AWS S3. S3 has some non-limitation where it can only listing 1,000 objects of a given prefix per request. We can try to improve this by either reducing the number of files on the file system or number of the files tracked by Iceberg metadata, which kind of lead us to the next slide on the data compaction. Raj, can you go next slide? Cool. So Apache Iceberg offer a way to stream data into the table with a high parallelism. However, this oftentimes introduces another problem called small files. Compacting many small files into large together with sorting will improve the table read performance. Reducing the number of files tracked by the Iceberg means less time spent on the open and close files. Currently, the data compaction allows us for granular controls so that we can instruct to optimize one partition at a time instead of everything in a given table. However, data compaction will create a larger files in a new snapshot, but it doesn't clean up the old one. In order to actually reduce the number of files on the file system, we will still need next expire snapshot action to handle the destructive parts. Snapshot is the Iceberg primitive to track off the data change. So it enabled the beloved time travel feature to allow the data consumer to go back in a time in the past and evaluating data at a given time step. However, this actually implies that whether or not to delete a given file now become much more complicated, because these can be potentially used by old snapshot and user need to time travel. So what we know here is that file can only be removed if it's not referenced by any metadata. The snapshot expiration come to rescue where expired snapshot is being identified first based on the time, and then the files only reachable by such expired snapshots are deleted altogether. So take previous data compaction examples, we can see that after compactions, the manifest M2, the data file D2 and D3 marked in red, these can be safely removed when we experiment the old snapshot S1, because all these metadata and data files can only reach by such a snapshot. If we expire them, then they're safe to be deleted. Next slide, please. So looking at the size distribution of our table under management, we realize there's a few interesting findings. The tables are like marine animals. There are hordes of anchovy or small tables with very little throughput and get used maybe once or twice a week. There are some tables with extremely high throughput and resource hungry for optimize, like whales. They're typically 10 or 100 times larger than average table we found in the catalogs. So it's important to group them into different silos, where we can allocate corresponding CPU cores and memory for optimization and schedule them as different cadence to meet our optimization expectations and avoid the resource contentions. Next slide, please. So as we can see here, when we building the Iceman as the smart table optimizers, we take scaling as one of the biggest challenge. We need to think about the table, how many tables are we currently managing? And also given the rate of growth, how are we going to scale our system by 10-fold or even 100-fold? So as we can see here, we can see data plane is much more workload heavy. So we start by thinking about how to scale our data planes. We separate these tables under management into a logical group we call silos. So for the silos, there's no overlapping tables across them. And we can scale our data planes by simply add more silos. And on the other hand, we can see that there's control plane might be the potentially bottleneck. So if the data set demand a physical separation, or we need to scale our control planes, we can build a new control plane, a new account to scale the entire system. So with both silos and account as our scaling primitive, I believe this is a way for us to see our system scale in next years and in the coming decades. So that's what I have. I would like to pass back to Raj.
Thank you, Steve. In this slide, I'll talk about some contributions we have done back to upstream. We highly dependent on open source technologies. We also a strong believer of contributing back. So we have branched out the open source, but we have done some internal changes to it to fit into our use case, and some optimizations to make sure that it runs at Apple scale. We're continuously providing commits with these features updates, bug fixes, and specs about how this Iceberg should look like in coming years. In the last quarter itself, we have done like 20 plus commits. I've listed few here. I won't go deep into that, but I'm happy to talk if anyone has any questions. With that, yeah, that's the end of the talk. Thank you, everyone.